Hi folks, CodeTutor here and my name is Anil Deshpande. Welcome back to the Artificial Intelligence Orientation series. In the previous video, we covered the fundamental concepts behind what is machine learning, what it means to mimic human learning, what is artificial neural network, how it mimics biological neural network, how these concepts led to the emergence of machine learning as a field built on the foundations of applied statistics. What we covered was just the tip of the iceberg. Now it is time to dive deeper into machine learning itself. Broadly speaking, machine learning can be categorized into four types: supervised learning, unsupervised learning, semi-supervised learning, and reinforced learning, or also called as reinforcement learning. We will start with the first and probably the simplest type, that is supervised learning. Let's start with something familiar, that is normal programming. Here we write the function, which is the code. We provide a set of inputs to that particular function. We decide what output is expected for a given set of inputs. This process is straightforward and predictable. However, in supervised learning, this process is inverted. Here we have an artificial neural network that performs the learning. We provide the inputs to this neural network and we also provide the output, that is expected output, to train it to produce the expected outputs. By doing this repeatedly with fine-tuning and using a good dataset, we obtain a function that can produce the expected outputs given similar inputs. In traditional programming, you write the code or function to generate the expected output. In supervised learning, you obtain the function that can generate the expected results when given inputs are similar to the training samples. The inputs are called features. The outputs, which are also the inputs to the neural network, are called as labels. The function which we derive is the model itself. You would be wondering, why is this called supervised learning? Because we are providing both features, that is the input data, and labels, the expected output, we are essentially guiding the learning process for the model. We are supervising the learning process. This guided learning approach is why it is called as supervised learning. So, what are some examples of supervised learning? For instance, consider a model trained on historical data that includes features such as plot area, locality, infrastructure in the locality, and state of the economy, paired with the price of the house as the label. Once trained, this model can predict the price of a house for new input samples with similar features. There can be more such examples. Based on the historical data of stock price, trade volume, and other economic indicators, you can do stock price prediction. Based on historical data of sales and marketing spend, you can do sales forecasting. Based on historical data on temperatures, rainfall, weather conditions, we can do weather forecasting. We can see that there is a pattern here. In this supervised learning, we are trying to predict continuous outcomes. The goal is to establish the relationship between the input features and continuous target variables. This comes under one specific category of supervised learning called regression models. But then there are another kind of supervised learning where you are trying to classify the items. For example, spam detection. Based on keywords in an email, you may want to determine whether it is a spam or not. Sentiment analysis. Based on a collection of reviews for a movie or a product, you may want to capture overall sentiment, whether positive, negative, neutral, about the product. Medical diagnosis. Based on the diagnostic scan image, you may want to predict whether cancer is present or not. All these examples involve classifying items into one or more categories. This type of supervised learning is known as classification models. Regardless of how powerful both these supervised learning models are, there are limitations to this approach. The top two limitations are dependency on the labeled data. Supervised learning requires a significant amount of labeled data to train the models effectively. Obtaining and labeling this data can be time consuming and expensive. The second top limitation is risk of overfitting. Supervised learning models, especially the complex ones, can overfit the training data. This means they may perform very well on training data but poorly on unfamiliar data, as they have learned to capture only specific details based on the training data rather than general patterns. Now that we have explored the powerful technique of supervised learning, let's shift our focus to another fascinating type of machine learning, that is unsupervised learning. Unlike supervised learning, unsupervised learning deals with unlabeled data. If we try to redraw the diagram for unsupervised learning, we see a slightly different structure. Here we have a model that is trained on features which are essentially our sample input data. Unlike supervised learning, we do not provide the labeled outputs. Instead, the model analyzes the input data to discover the patterns and structures within the data. Through this training, the model learns to identify and group similar data points, helping us to uncover the hidden insights from the data. What does it mean to have this kind of model, and what kind of problems does it solve? Customer segmentation. You can supply this model with customer data and it can identify groups of frequent buyers. By analyzing purchasing behavior and other features, the model uncovers the patterns that help to segment customers into distinct groups, allowing business to tailor the marketing strategies and improve customer retention. Another example is fraud detection. You can supply this model with bank transactions and it can detect patterns to recognize fraudulent activities. By examining transaction details such as amounts, locations, and frequencies, the model identifies unusual patterns or anomalies that can indicate fraud. Unsupervised learning models are powerful because they can uncover hidden patterns and structures in data without need for labeled outputs. As you can see in both examples we just discussed, we are grouping or clustering the sample data to identify patterns. This type of unsupervised learning is known as clustering models. However, there is another category of unsupervised learning called dimensionality reduction, which addresses different types of problems. In case of dimensionality reduction, a large data set is supplied to the model. The model can then summarize the data into simpler, more comprehensible form while preserving the essential information of the original content. What do you mean by this? Take for example e-commerce. You can recommend products to customers based on their previous browsing history and purchase history. Streaming platforms. They can suggest movies based on the past viewing behavior of the audience. In these cases, the model uses a large data set to identify key patterns and reduce the data to its most relevant features, which is why it is called as dimensionality reduction. But these unsupervised models have limitations as well. The first one, lack of ground truth. In unsupervised learning, there are no labeled outputs to guide the model, meaning there is no reference point to validate the accuracy of the identified patterns or clusters. Without labeled data, it's challenging to assess models' performance and meaningfulness of the discovered patterns. For example, in customer segmentation, an e-commerce company might use unsupervised learning to segment customers based on purchasing behavior. The algorithm might group customers into clusters based on purchase similarities. However, without labels like high value customers, frequent buyers, it is difficult to verify the accuracy and usefulness of these clusters for marketing strategies. The company might actually end up with segments that don't align with actual customer behavior and business goals. The second limitation is difficulty in interpreting the results. The results of the unsupervised learning models can be hard to interpret, especially with complex algorithms. Understanding the significance of the discovered patterns and how they relate to the original data can be challenging. For example, document clustering. An organization might use unsupervised learning to cluster large collection of documents into various topics. The algorithm groups documents into clusters, but understanding what cluster represents can be difficult. Without clear labels, it's hard to determine the significance of each cluster and how to use the information effectively. That is where we come up with a hybrid approach combining both supervised and unsupervised learning. Not surprisingly, this approach is called semi-supervised learning. In this case, we have a neural network that produces a model capable of recognizing the patterns. The key difference is that these models are trained using both labeled and unlabeled features. If you are wondering about real life applications of semi-supervised learning, Google Photos. Initially, the app asks you to tag people in few photos. Once you do this, it can identify the same people in untagged photos using the pattern it learned. The labeling was provided by you initially. Speech recognition in the audio industry. Semi-supervised learning is widely used for speech recognition, combining a small amount of labeled audio data with a large amount of unlabeled data to improvise accuracy. Once again, it's not like this doesn't have any limitations. The top limitation is dependency on the labeled data. Semi-supervised learning still requires some labeled data to guide the learning process. This shares the same limitations as supervised learning, where obtaining and labeling the data can be time consuming and expensive. And the second one is complexity. Semi-supervised learning models are more complex to design and implement than purely supervised or unsupervised models. This complexity arises because the model must effectively use both labeled and unlabeled data, often involving sophisticated algorithms and careful tuning to balance their contribution in the final outcome. Other than these three learning mechanisms, there is one more class of machine learning called as reinforcement learning or reinforced learning. It might sound intimidating, but it's not. Let me explain it with an analogy. Think of it like a dog training. When you give a command to an untrained dog, it might not understand it at first. If it doesn't obey, you withhold its favorite treat, which is a negative in reinforcement. When it learns to sit, stand, or behave well, you reward it with treats, that is positive reinforcement. You are reinforcing the behavior you want to see in the dog through the actions and rewards. Both can be positive and negative, and that is how you basically train a dog. Let me remove the images of the dog because they are too cute and distracting from concentrating on learning the topic under discussion, that is reinforced learning. Now let's translate this into technical jargon. The dog is the agent. The environment is where the agent operates. Agent performs an action. This action changes the state of the environment. From this new state, we determine if the outcome is good or bad for the agent, that is positive or negative reward. The new state and the positive or negative reward are fed back into the agent, allowing it to adjust its behavior for better results next time. This is a continuous loop. Looks pretty straightforward, but you might be wondering, where does the machine learning model come into the picture here? Well, the agents host the model. It can be more than one model. There might be a policy model or a value model. These models define what actions the agent can take and help determine the best parameters for operating effectively. The best examples that come to mind are autonomous vehicles and robotics. They continuously operate in an environment governed by certain policies, and based on outcomes, they keep improving themselves. And once again, in this case also, there are limitations. The first limitation is limited sample data size. Reinforcement learning requires large amount of data from interactions with the environment to learn effectively. Take for example, in case of autonomous vehicles, gathering this data can be challenging and expensive. For example, testing an autonomous vehicle on real roads to collect diverse driving scenarios involving significant time, cost, and potential safety risks. Limited data can hinder the model's ability to learn. The second limitation is stability and suboptimal solutions. Reinforcement learning algorithm can be unstable and may not always converge to the optimal solution. In autonomous vehicles, this instability can manifest as inconsistent driving behavior. For instance, a vehicle might learn a suboptimal policy that performs well in some driving conditions but poorly in another, leading to unsafe maneuvers or inefficient routes. Ensuring the stability and optimal performance across all scenarios can be a significant challenge. As we discuss these various machine learning techniques and their applications, many of us might now realize how we have already been using these without realizing that these things are actually being applied behind the scenes. Some might also believe that these advancements have only occurred in last couple of years. However, this is not true. These developments have a long history. To properly appreciate it, let's have a quick overview of timelines at the evolution of these technologies and its applications. The early conceptual foundations of machine learning were laid in 1950s. From late 1960 to early 1970, there was a period known as AI winter or artificial intelligence winter, where progress slowed significantly. The code contributed to this stagnation as mutual suspicion between scholars from opposing camps hindered collaboration. Major breakthroughs occurred from 1970s through 1990s. From the 2000 onwards, we began to see the emergence of real applications of these advancements. We now have a good foundational knowledge of machine learning. In the next video, we will explore the next major breakthrough in machine learning, that is deep learning. Stay tuned. That brings us to the end of this particular video. Don't forget to like, comment, share the video and subscribe to the channel. Take care. Bye.